Bismillahirrahmanirrahim. Today, inshallah, we shall talk about parallelogram theorems and their proofs. Before we get going, however, I'd like to introduce you to 4 new students that we have in our class. They are right here. Welcome to class, gentlemen. Curiously, these guys, they don't seem to take off their helmets. But nevertheless, welcome to class. If you recall, last time we talked about these theorems. We just got ourselves acquainted with these, and I said next time we should try to prove them and do some examples with them. So these were theorems related to parallelograms. That is, what we were told is that we were given a parallelogram, and if we were given a parallelogram, we could make certain conclusions. That is, the starting point for all of these theorems, that we were given a parallelogram. And if you recall, the definition of a parallelogram is very important to appreciate, and it's really in the name of the word parallelogram itself, and that is, a parallelogram is a quadrilateral with 2 pairs of parallel sides, 2 pairs of parallel sides. So if we were given a parallelogram, and I said all of these theorems start out with that given information, that is, we have a parallelogram. If you're given that, then we can make certain conclusions about this particular quadrilateral. So they're all, the first 4 start at the same, and the last one starts slightly different. So let's just review. If a quadrilateral is a parallelogram, see this, and then if a quadrilateral is a parallelogram, if a quadrilateral is a parallelogram, if a quadrilateral is a parallelogram, so they start the same way. The last one slightly differently. One additional criteria: if a parallelogram has a right angle. So that's the only one that's slightly different wording. But nevertheless, the first 4 at least, they start the same way. If a quadrilateral is a parallelogram. So if we're given a parallelogram, basically, then we can make the following conclusions. Then its opposite sides are congruent. So if we're given a parallelogram, then we can say that the opposite sides are congruent. And secondly, then we can say then its opposite angles are congruent. Then we can say its opposite angles are congruent. And thirdly, we can say the consecutive angles are supplementary. They are supplementary. The consecutive angles, C-O-N-S, consecutive. I do that terribly here. I have audience now. I have to be careful. So consecutive angles are supplementary. So consecutive means any 2 adjacent, like in a row, so right next to each other. Consecutive angles are supplementary, that they add up to 180 degrees. And fourthly, that the diagonals bisect each other, and that's very important, beautiful. And that is, the diagonals bisect each other. That is, they cut each other in half. The purple is cut in half. The brown diagonal is cut in half, so diagonals bisect each other. And the last one is worded slightly differently, as I said, and is that we're still given a parallelogram, but we're given a parallelogram with one specific special qualification. That is, if a parallelogram has 1 right angle, then it has 4 right angles. That is, if you're told that this is a parallelogram and it has 1 right angle, then it has 4 right angles. So if there's 1 right angle, then we have 4 right angles. That's the theorem, and these are actually reasonably easy to prove, and that's what we shall try to do today. We shall try to prove these theorems, and they're beautiful and easy proofs in my mind, inshallah, and that's what we're going to do next. Now, before we do any of these proofs, however, we have to really understand and remember, recall, and review the postulate and theorems that we learned about parallel lines. If you recall, we had theorems that started like if 2 parallel lines are cut by a transversal. So those are postulates and theorems that we really have to know, because all the proofs for these actually is based on those theorems. Because a parallelogram is like a haven or heaven for parallel lines. Because if you have, for example, I've drawn a parallelogram here. It's basically you have one set of parallel lines, and there's a transversal here, and then a transversal here, and then there's another set of parallel lines with transversals. So if these are parallel lines here, and there's a transversal here. So in proving parallelogram theorems, you're using parallel lines and transversal postulates and theorems. So the first order of business to make sure that we understand and review those postulates and theorems. So I've drawn over here these two lines, the white lines, and then this purple line, the transversal. Now you can have lines and transversals without them being parallel. In fact, here we can't assume that these white lines here are parallel unless we are told that they are parallel. So here I have made no indication that they are parallel. But if I go like this, if I put these two symbols over here, then we know that these two lines are parallel. So we have to be careful what we assume, and that we can't always assume lines being parallel. We have to be told that they are parallel. Now, if two parallel lines are like this, and they're cut by this purple line, which is called a transversal, I mean, cutting through goes through, traverses these two parallel lines, then we create a bunch of angles. Specifically, I can label these angle number 1, let's say 2, and 3, and 4, and then 5, 6, 7, 8. So we have these 8 angles that are created, and we have to we have given some special names to these angles. And the most important of these, as a starting point, for example, was this angle 2 and angle 6. If you come with angle 2 and angle 6, these were corresponding angles. Okay, so these were called corresponding angles. These are not the only corresponding angles here. There's 4 pairs of them. For example, 1 and 5 were another pair of corresponding angles, and so were 3 and 7 were corresponding angles, and 4 and 8 were also corresponding angles. So there's four pairs of these corresponding angles. It means their geographic location, meaning one on each side of the parallel line. So those are corresponding angles. The second set of angles was these angles, which apparently ended up being very, very important. These are alternate interior angles. So these are alternate interior angles. Now this is just a review, so I'm assuming you know these reasonably well. So those are 3 and 5 are alternate interior, and then there's 4 and 6 are another pair of alternate interior angles. So there's 2 pairs of alternate interior angles. And also, we have alternate exterior, like 1 and 7 are alternate exterior angles. So there's alternate exterior angles, okay? And finally, we have another set, and that is consecutive interior angles. And that's these two over here, inside, consecutive interior angles. Those are consecutive interior angles. Consecutive mean right next to each other. So these two here, maybe I could just use a nice yellow here. 3 and 6 are consecutive interior angles. So we have consecutive interior angles. Consecutive means right next to each other. So those are that's a consecutive interior angles. 3 and 6, and 4 and 5 is another pair of consecutive interior angles. And these are very, very, very important to appreciate, okay? Because these are the theorems here, and postulate and theorems here are the ones that we're going to use to prove parallelogram consecutive interior angles. So there are 4 important angles that are generated when you have a parallel line cut by a transversal. Now that's very important, but we can't also forget some basic other basic angles that are also generated. So I'm going to just redraw these parallel lines and this transversal, and don't forget the vertical angles here. For example, this one and this one. So those are vertical angles. The vertical angles are very important, like gifts in geometry, because we know vertical angles are congruent. So don't forget those vertical angles. And here's another vertical angle. So vertical angles are very important. Don't forget those. And also don't forget supplementary angle. These 2 angles are supplementary. Let me just label here again. Angle 1 and 2 are supplementary, right? Because in fact, they're special kind of supplementary angles. They're called linear pair. So you can have supplementary angles that are right next to each other like this, or you can have supplementary angles that are not attached to each other like this. So you can have like for example, this is 120 and this is 60, and this is 120 and this is 60. These 2 are also supplementary, but they're not sitting next to each other, right? But supplementary angles that are sitting next to each other are called linear pair, a special category of supplementary angles. So anyway, that's basic review that I hope that you already knew. So don't forget the vertical angles and supplementary angles and linear pairs, all of that stuff. That's kind of important. But if you recall from here, we had a whole bunch of postulates and theorems. There was one postulate and there are a bunch of theorems, basically, stated as conditional statements. So they all started out like this: if two parallel lines are cut by a transversal, so they all start like this: if two parallel lines are cut by a transversal, in this case it's a transversal. And then we had a whole bunch of conclusions. Then we had stated, for example, all of this. Then we had stated that the corresponding angles, that's 2 and 6, the corresponding angles were congruent. And we also said the alternate interior angle, like 3 and 5 over here, they were congruent. And then we said alternate exterior angles were congruent. And finally, the consecutive interior angle, like these inside ones, the consecutive interior angles were supplementary, right? So now these are very important to remember, review in turn to demonstrate the proofs for parallelograms. Now the first of these, the corresponding angles one, that was a postulate. So corresponding angles being congruent, that was a postulate, and the rest of them were theorems. So postulate, theorem, theorem, theorem. So if two parallel lines are cut by transversals, then the corresponding angles are congruent, postulate. If two parallel lines are cut by transversals, then the alternate interior angles are congruent, theorem. If two parallel lines are cut by transversal, then the alternate exterior angles are congruent, theorem. If two parallel lines are cut by transversals, then the consecutive interior angles are supplementary, theorem. Okay, so that we have to really get to know very well, and in the next lesson we have to actually use the same but the converse of these theorems to prove additional parallelogram theorems. So that is a very important starting point for this lesson. The next thing is that we have to connect these two concepts. That is, we have to connect the idea of parallel lines cut by transversals and all the postulates and theorems to parallelogram. That is, when we see this particular picture, you should be able to see this particular picture. Or when you see a parallelogram like this, you should be able to see this parallel lines and transversals like that. Because the definition of parallelogram is that you have parallel lines, right? So when you see a parallelogram like this, you understand that there are parallel lines like this, and there are two pairs, in fact, like as I said, it's like a gift, like the parallel lines like this. So when you see a parallelogram like this, you have to be able to envision all the postulates and theorems that relate to parallel lines and transversal. So if I have a parallelogram like this, you should be able to imagine in your mind's eye transversal and parallel lines and transversal. For example, you should be able to superimpose these two pictures kind of like this. So you have two parallel lines and a transversal like this. So one of the sides here, the left side is going to be the transversal, and the top and bottom sides of the parallelogram are going to be like the parallel lines. And then the fourth side is kind of like in your mind's eye, it's there, but it's not playing into action in here. Or alternatively, you can see you have two parallel lines like this, top and bottom, and the right side acts like a transversal. And then we can use all the theorems in that way. For example, if you have these two parallel lines, that's transversal, then these two are going to be consecutive interior angles, right? Because, parallel lines, transversal, consecutive interior, and we already know the consecutive interior angles are supplementary, and that's actually what we know to be true for parallelograms. So if you see parallelograms, you should be able to see parallel lines and transversal. And the other way too. Now, in the first scenario, the top and bottom sides of the parallelogram acted as parallel lines. Here, the two sides are acting like parallel lines, and the top side is acting like a transversal. So here we have two parallel lines going like this, and the top side is acting like a transversal. Or we could have it the other way. The bottom side can act as a transversal, and the two right and left sides can act as parallel lines. So parallel lines and transversal like this. So the idea here being that when you see a parallelogram, you should be able to see all of these different scenarios of parallel lines and transversal. And that's particularly important because that's how we're going to prove the theorems regarding parallelograms. Okay, so armed with that bit of knowledge, let's see if we can try to prove, starting with the first theorem here. If a quadrilateral is a parallelogram, then its opposite sides are congruent. We're going to try to prove that particular theorem. Okay, so here we go. I have set up a proof over here. It says given ABCD is a parallelogram. Now this is a symbol of a parallelogram. It's kind of like this. That's supposed to be a symbol of a parallelogram. So we're given that ABCD here is a parallelogram. If you recall, polygons very easy to name. You just trace out the vertices, and that's how you name it. This is parallelogram ABCD. So we're given that. So, and that's not a trivial amount of information that's given. That's actually a lot of information that's given. If you know this is a parallelogram, then you know that by definition that the opposite sides here are parallel like this. So that's what's given to us, and that's actually a wealth of information that's given. Now, if we are asked to prove over here that basically that the opposite sides are, let me get rid of this so it doesn't get too cluttered. We are asked to prove that AB is congruent to DC. We are asked to prove that this side is congruent to this side, AB is congruent to DC, and then we are asked to prove that AD, which is this side over here, is congruent to BC over here. So that's what we are asked to prove. Now the question is, that's a pretty tall order, and how am I going to get those sides to be congruent? So that's what we're aiming for. But all we know so far is that these are this is a parallelogram. That this side is parallel to this side like this, and this side is parallel to this side. And again, the goal is to prove that the opposite sides being congruent. How am I going to do that? Well, the trick is this, and this is actually a very lesson in the trick itself. So what I'm going to do here is we're going to connect these two opposite vertices like this, and construct a line, construct a diagonal, or draw out the diagonal like this. What that does is that gives us two triangles now, right? We have two triangles inside of this parallelogram. Triangle number 1 and triangle number 2. This triangle over here and this triangle over here. So we have constructed two triangles by drawing this diagonal. And that, as I said, is an instruction in itself. That is, triangles in geometry are one of the most fundamental figures. They're the simplest two-dimensional figure, right? Because there's nothing smaller than a triangle in terms of a polygon. So the smallest polygon is a triangle, right? It's the simplest polygon. It's very useful, very versatile polygon. So there's a triangle, there's a quadrilateral, there's a pentagon, hexagon, heptagon, octagon, etc. But the triangle is the simplest polygon, and we know a lot about triangles. In fact, right? We can prove them to be congruent. We can prove them to be similar. We know a lot about their sides. We know about the angles. So triangles like the workhorse of geometry. You can do a lot with triangles. Well, what are we going to do over here? Well, if I could prove that these two triangles are congruent, then I could say that the opposite sides here are going to be congruent. How? Because if these two triangles are congruent, then I can say corresponding parts of congruent triangles are congruent. Corresponding parts of congruent triangles are congruent. CPCTC, you gotta know that. So corresponding parts of congruent triangles are congruent. That is, if you can prove two triangles, if you were given two triangles are congruent, then you know if they're congruent. That's the definition of congruence. If they're congruent, then the corresponding parts, darn it, they have to be congruent like this. If these two triangles are congruent, then the corresponding sides are congruent, and not even just that, the corresponding angles are also going to be congruent like this. You follow what I'm saying? So it's very important that if you understand that if you prove two triangles to be congruent, that gives you a lot of other information, a lot of baggage that comes with it. All the corresponding parts, including all the sides, corresponding sides, and all the corresponding angles are going to be congruent. So if I could prove that these two triangles, triangle 1 and 2 that I have constructed in the parallelogram, are congruent, then basically I'm done, because then I could say that the curve AB is congruent to DC because they're corresponding parts, and AD is congruent to BC because there are corresponding parts. No, so objective here now for me is to prove that these two triangles are congruent. Now, how do we prove triangles to be congruent? Now, that's the key. How do we prove triangles to be congruent? Now, if you don't know this, I don't know why you should not know this, but if you don't know this, you have to understand it's not that many ways. Really, it's not that many ways you can prove triangles to be congruent. And here it is, S, right? Side, 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 angle, side, angle, and then angle, side, and then there's a hypotenuse leg, but that's only for right triangles, right? So those are really the essential ways that we prove triangles to be congruent. And yeah, you have to know this. So if in any time you're going to try to prove triangles to be congruent, you're going to go back to those side, angle, side postulates and theorems. So that's how we're going to use. Somehow we have to demonstrate these two triangles to be congruent using these, and we're not going to use hypotenuse leg because I don't see any right angles over here. So there are really 4 ways. So if I was trying to demonstrate these two triangles to be congruent, like these two, 1 and 2, to be congruent, we have to get at least one side, because if you notice, if you remember from our prior discussion, all of these have at least one S in them. You know what I'm saying? You can't get away with it. You have to show somehow that there's one side that's common to both of these triangles that's congruent, okay? So triangle 1 and triangle, if you want to prove them to be triangle, you have to prove what one of the corresponding sides, like this one and this one, are congruent, or this one and this one are congruent. But that's what we're trying to prove, though, right? Okay, well, let's see. Now, and then we have to get some angles to be. So we have to get some angles congruent. We have to get some sides to be congruent. How are we going to do that? Well, if you appreciated from a discussion before, we learned a lot about parallel lines and transversals. So, and if you, as I said, if you had parallel and transversal, you can get a whole lot of angles to be congruent, right? Because here's parallel lines, here's transversal. Aha. Because if you can see this parallel lines and this transversal right here, if I would just extend this side, the top sides like this, watch this. If I were to just extend that, okay, so I have a parallel and transversal. If I were to do that in your mind's imagination, then you understand that these two angles right here are congruent. That angle is congruent to this angle because that's alternate interior angles like this. Oh my goodness, so we just have one set of congruent angles right there. Right? So those are alternate interior angles. In the same way, so those angles are congruent. That's really, really cool. Right? And in the same way, I can get these angles to be congruent like that. So those angles are congruent. How? Because I have parallel lines. That's this one and this one. Those are parallel lines. And then they're cut by a transversal. In this case, right here. Using the same transversals, the same line here, I can say that this angle is congruent to this angle because they're alternate interior angles. If two parallel lines are cut by a transversal, then the alternate interior angles are congruent. That's amazing to me, because using one diagonal, right? And there are two diagonals in every parallelogram. Just using one diagonal, we have proven that those angles are congruent. That's amazing. That's a lot of information that we got. That's all from the definition of parallelogram, that the two opposite sides are parallel. Okay, wow, that's quite a bit. So we have two angles already. So we can use that. We can even use this if we have that. But it looks like we've got two angles. Now we have to get one side. Now which side are we going to be able to get to be? Well, we can't get A and B and D, C because that's what we're trying to prove, and we can't get A, D, and B, C because that's what we're trying to prove. But then you see that DB is common to both triangles, like this, right? That's the shared side, okay? Wow, now we have angle, side, angle. Now you have to be careful. You start out with you start with the yellow angle, go to the side, and then go to the white angle. So you have to go in the corresponding way. So yellow angle, side, and this angle. So we have angle, side, angle. So we can use angle, side, angle to prove those two triangles congruent. So using angle, side, angle, we can prove, say, triangle, start with A. Okay, triangle A, and then we can go to we can go to B. Triangle A, B, and D. Triangle A, B, D. Triangle A, B, and D is congruent to triangle. So we have to start with A. We have to start with C. Triangle C, and then look, we went from A, we went to B. So you have to start with C. You can't go to B. You have to go to D because you have to go to the right corresponding angles. So triangle ABD is going to be congruent to triangle CDB. CDB. You can't say CBD. That would be wrong because ABC corresponds with triangle CDB. So there it is. So we can use angle side angle to prove those two triangles to be congruent. And once we've done that, we're done. We can say once we've done that, we can say that AB is congruent to DC because of CPCTC, and we can say that AD is congruent to BC also because of corresponding parts of congruent triangles are congruent. And that's how we get this proof done. So what did we have to realize to get this proof done? We had to construct a triangle inside of a parallelogram, the two triangles, and we had to prove them to be congruent. And we said there are really 4 ways here, and except we're not going to use the hypotenuse leg, which is the 5th way, because we don't have a right triangle. So we recognized we had to use those to prove. And then to get those angles to be congruent, we used the parallelogram theorems, alternate interior. We got 2 angles congruent, and we recognized that DB is darn it congruent to DB by a reflexive property of congruent segments. And we used angle side angles to prove the congruent, those 2 triangles congruent. And by CPCTC, we have those corresponding parts to be congruent, which was the goal of the proof. So there you have it, and that's the proof. Now you recognize here we proved the first theorem that we had to do, and then the same proof also can be used. In fact, once you've proven those 2 triangles to be congruent, can't you say angle A is congruent to angle C because they are corresponding parts of congruent triangles? Yes, by the same theorem we can also say angle A is congruent to angle C because of corresponding parts of congruent triangles are congruent. In fact, we can prove that the opposite sides of a parallelogram are opposite angles of parallelogram are congruent using the same proof. So you do the whole thing the same way, except over here you can also say angle A is congruent to angle C because of corresponding parts of congruent triangles are congruent. So we can use the same proof to prove that A is congruent to C. But then you say, well, what about B and D? Well, you can also prove those to be congruent by just drawing the other diagonal, because if you have this parallelogram, as I said, there are 2 diagonals. I drew this diagonal for you, like this, but then there's another diagonal, right? Here's another diagonal, like that. You can draw that diagonal and you create 2 different triangles, and then you can prove those to be congruent by the same process. So you have, these are alternate interior angles, like this, and then these are also alternate interior angles, like this, and then you have one side that's shared between them, and then you have angle side angle, ta-da! And then you can prove these 2 angles to be congruent. So you can just draw the other diagonal and go through the same process. It just so happened that I drew that particular diagonal. So by doing this proof, in fact, we have shown 2 things. Let me show you what we have done so far. Using using that particular proof, we have shown that the if a quadrilateral is a parallelogram, then the opposite sides are congruent, opposite angles are congruent by CP/CTC, right? Opposite sides are congruent, opposite angles are congruent. So we have done 2 proofs so far for parallelogram. Well, what about this third one, you say? Okay, what about this third proof? How do you prove this? And that's actually quite easy to prove, this particular one where the consecutive interior angles are supplementary, because that's kind of easy, because if you have a parallelogram, then the opposite sides are parallel like this by definition, right? And then what do we know about consecutive interior angles of parallel lines and transversals? So if I have an x and y over here, if 2 parallel lines are cut by a transversal, then the consecutive interior angles are supplementary. And that's a consecutive interior angle theorem. So it's very easy to prove that the consecutive interior angles are supplementary in a parallelogram, because of parallelogram being 2 pairs of parallel lines. Now, this particular proof, the fourth one, is slightly different from the rest of them, and we shall get to that in just a second. This last one over here, if a parallelogram has 1 right angle, then it has 4 right angles. It's very easy to prove because of the consecutive interior angles again. So if this is 90 degrees, then these are supplementary, so that has to be 90 degrees. And if that's 90 degrees, and that's a transversal, then this is 90 degrees. Consecutive interior angles are supplementary. And then same thing over here. So this last one is also very easy to prove. So the only other one that is with the diagonals is slightly different than the other ones, which I shall try to demonstrate next, inshallah. Okay, so our goal here is to prove that the diagonals bisect each other. That is, if we are given that we have a parallelogram, then we are supposed to prove that the diagonals bisect each other. Okay? That's what we're trying to prove. Now, you have to be very careful here that what this means. That means that this diagonal, the purple diagonal, is cut in half like this, and then the brown diagonal is cut in half like this. It does not mean that the diagonals are congruent to each other. In fact, they're not congruent to each other. It can't be. Let's see if you can appreciate that. The diagonals here cannot be congruent. Why? Well, let's see. If I were to draw out this triangle over here, I'm going to draw this triangle over here like this. Here it is, the first triangle. Like I drew out that triangle. Okay, so if you have that triangle over there, and then if I were to draw out this other triangle over here like this, with the purple diagonal like this, okay, we already know that the opposite sides of parallelogram are congruent, right? So from the theorem that we just demonstrated. So we know this side is congruent to this side. We know this side is congruent to this side, okay? So those 2 sides are congruent. Now here you can see clearly that like this is an obtuse angle, at least from the way it's drawn, and this is an acute angle, right? So we know from the hinge theorem that the side across from the bigger angle is bigger and than the side across from the smaller angle, correct? So in fact, this purple side is smaller than the brown diagonal, because of the hinge theorem. So big mouth, big lid theorem for 2 triangles, right? Because it says the side across from the bigger angle is bigger than the side across from the smaller angle. So the first thing you have to understand that these diagonals are not congruent. In fact, they can't be, and that's easy to prove from the big mouth, big lid theorem or the hinge theorem for 2 triangles. Anyway, so that's very important to understand. The diagonals are not congruent, but they bisect each other. In other words, this is a midpoint. This point right here is a midpoint to both of them. Well, let's label this again. Let's label this parallelogram A, B, C, D, and we can label this one here. Let's call that point M, since it's kind of like the midpoint. Okay, so we have to demonstrate that now that if this is a parallelogram, the diagonals bisect it. So our goal is to prove this particular figure, that this is congruent to this, and that this little segment is congruent to that little segment. So how are we going to do that? Well, it's all in the picture, I think. If you could demonstrate, for example, if you could demonstrate that this triangle here is congruent to this triangle, okay? that the top, the smaller triangles are congruent, then you could do CPCTC, can't you, man? That CPCTC is very, very important. Or if you could demonstrate this triangle to be congruent to this triangle, then you can use CPCTC to demonstrate that. Now, how are we going to be able to do that? Well, there are only 4 ways, again, to prove triangles to be congruent, right? You have side, 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 you have side, angle, side, angle, and angle, side. And there's hypotenuse, left, or right triangles, right? So we're going to use those to prove these 2 triangles to be congruent, right? So, but here we have to be careful that we don't know that these are congruent, right? So we can't assume those to be congruent. So let me take those out. Let me take these tick marks out. So let me relabel this here. So this is A, this is B, and this is C, and this is D, and that's called that point in the middle, point M. So we're at our goal is to prove. So our goal is to prove, we're given a parallelogram, prove that AM is congruent to CM, like this. Segment AM is congruent to segment CM. That's our goal. And we are to also prove that segment DM is congruent to segment BM, like this. Okay, so that's our goal, right? They bisect each other. All right, so the way we're going to try to prove that is we're going to prove triangle 1 is congruent to triangle 2, or alternatively, this triangle at the top is congruent to triangle on the bottom. Then we're going to use CPCTC. Well, how are we going to do that? Well, same way. The parallelogram gives us a lot of stuff, right? We get angles left and right. So, well, we know this angle is congruent to this angle because that's alternate interior angle theorem, because this is the pair of lines, and that's a transversal. Those are alternate interior angles, like that. Okay, so you have to be able to see those alternate interior angles. So we got those alternate interior angles. Okay, and also now I got this alternate interior angles, correct? Yes. Now what else? Well, I know these are vertical angles, but that's angle. That's, you can't use angle to prove triangles to be congruent. I need a side. I need some side, and I can't use this side because that's what I'm trying to prove, right? Those sides, right? What other side is left? Well, the only other side that's left is over here, like this. But we know those to be congruent because we just proved that. We can use the theorem that we just used, that if a quadrilateral is a parallelogram, then the opposite sides are congruent. We can use that theorem to prove this theorem. And that's perfectly legitimate, right? We can use one theorem to prove, we do it all the time. We can use one theorem to prove another theorem. Now that we know that the opposite sides are congruent, we can use that. And then we have angle, side, angle. So those 2 triangles are congruent by angle, side, angle. Angle, side, angle. Angle, side, angle. Ta-da! And we're done. And once we prove them to be congruent, angle, side, angle, then we can use CPCTC to say that this is congruent to this, and this is congruent to that. Ta-da! That's easy peasy. So let me write this as a paragraph proof. Okay? So we are given, so the given information here is that we have a parallelogram A, B, C, D. Okay. If we're given that information, you have parallelogram A, B, C, D. From there, you can get those angles to be congruent. So you have angle A, B, D is congruent to angle C, D, B, right? C, D, B, right there. So those are congruent, and we can say angle, this angle right here, D, I'm sorry, C, A, B. So angle C, A, B is congruent. C, A, B is congruent to angle A, C, B. Angle A, C, B right here. So those are alternate interior. These are alternate interior angles are congruent. Alternating angle theorem. So we got that. And then we can say, that AB is congruent to DC because of opposite sides of a parallelogram are congruent. That's a theorem that we just learned, that we proved, in fact. Okay, since we have that, from here we can say angle, side, angle, triangle congruence. Prove the triangle is congruent, and then we can clearly say AM is congruent to CM, and DM is congruent to BM because of CPCTC. CPCTC. Ta-da! Done. So as you can see, you can prove sides, you can prove angles to be congruent using triangles, which is a very versatile geometric figure, the most basic figure. If you want to prove something about polygons, pentagons, hexagons, whatever, you want a good recourse. A good are the triangles, and there are lots of theorems associated with them. So today we did a lot of work. Specifically, we learned a lot of theorems. We learned to prove a lot of theorems. We proved that the opposite sides of parallelograms are congruent. We proved that the opposite angles of parallelogram are congruent. We proved that consecutive angles of parallelogram are supplementary, and that the diagonals bisect each other. And finally, if a parallelogram has one right angle, then it has 4 right angles. And that's a lot of good work. I hope you appreciated and enjoyed it as much as I do. And again, welcome to our new students. Until next time, الصلاة والسلام على رسول الله والحمد لله رب العالمين. السلام عليكم.